Okay, so let me, so this week we have our very own Tiziano. I don't think Tiziano needs much of an introduction. He got his PhD from Bologna a while ago. Since then, he's held, he had an entire career at CERN where he held multiple responsibilities. He was Delphi spokesperson, CMS spokesperson. A couple of years ago, he moved to LEP, so he's now LEP. And he also became involved in the SND experiment, where he's now responsible for the coordinator for the upgrade, as coordinator of the upgrade of the experiment. But that's not what Tiziano will tell us about today. So we'll hear about LEP3. So take it away.
Okay, so the mic is the one of the.
The mic is there.
Okay, so I can stand.
Yeah,
I don't need to.
It's just the button there. Yeah.
So what I am here today is basically to report about some sort of effort which a group of concerned people have put together in order to submit a proposal to the process for the European Strategy Group. Now, the link is there if you want to see it, the document. There is also a rather long backup document which we are going to post on archive soon. So it's essentially about LEP3 is a proposal to reuse the LHC tunnel. Now let me tell you why we got together. It's simply because, just bluntly, we all know that that means this consensus building in the community about the future of energy physics in Europe, about building this big proposing to build this big collider, which basically would be over 100 kilometers machine, which is called the Future Circular Collider. First with the plus and minus program, and then with the proton-proton program. So repeating in bigger what has happened with LEP, LHC. And we know that there's consensus, but there is also people in the community which are worried about the fact that such a program could be, especially the cost of it is daunting. And so people are talking about backup solutions. Now, the reason why we got together is simply because we kept hearing about backup solutions, which were not really plan B. They were alternative plan A. Because if you don't find the money to build, if the reason why you don't build FCC is because you don't have enough money, you cannot propose another project which is the similar amount of money, okay? So, and also we took into account the fact that there's consensus in the community, but the fact that what we are really needing is something which allows us to fully explore electroweak scale as we know it, basically through building a Higgs factory. And in fact, as I said, the linear collider, for example, doesn't fit this definition. For us, a linear collider is a plan A, because I mean the cost of even the minimal configuration is 8 to 9 billion. But then if you really want to exploit it, you get to a cost. If you want to go to 1 TeV, you get to a cost which is the same as FCC. Now, this is the list of the people. So let me try to set the scene. The recommendation we start from the recommendation of 2000, or the previous strategy exercise. So their recommendation, I remind you, was to first really complete successfully the luminosity LHC. They were supporting strongly the fact of the neutrino platform and having a world neutrino program which would basically exploit as well this aspect of the high energy physics, which is still a lot of questions unanswered. An electron-positron Higgs factory is the highest priority next collider. So this really, I interpreted this being the Higgs factor is nothing but exploiting fully, I would say, the exploration of the electroweak scale. Then there is R&D effort focused on advanced accelerator technology, especially for developing the future generation of high gradient magnet devices, and then investigate the technical and financial feasibility of a future hadron collider at CERN with essentially with the square root of S of 100 TeV, everything plus or minus 6, and the electroweak factor as a possible first stage. Obviously, point T was already anticipating what is the FCC. The other thing is that I believe that one should interpret in terms of physics and research. The objectives which we have is that on one side, as I said, exploit fully and explore fully the electroweak scale. The other is that if you want to go beyond, you should have at least a factor 10. So the 100 TeV machine is something which basically explores a center of mass energy or an energy scale which is order of 10 TeV, as opposed to the 1 TeV, which is the electroweak scale, roughly speaking. Okay, so and I believe that about this there is roughly consensus in the community. There might be consensus on how to implement it, but this is how. So let's just say that this bunch of people, most of them retired, we support FCC-ee and FCC-hh as the preferred option for the CERN future. There's no question about it. When you look at the performance, that is, if you can afford it, that is the machine we should build. So LEP3 is not competitive with FCC-ee and not competitive with CEPC, for example, the equivalent collider in China, for example. So we believe that if CEPC goes ahead, then we would advocate that CERN proceeds to FCC-hh in as timeless manner as possible. For those of you who have been involved at all in writing any document for this present European strategy exercise, the guidance says that the strategy update should include the preferred option for the next collider at CERN, FCC-ee, FCC-hh for us, and prioritized alternatives options to be pursued if the chosen preferred plan turns out not to be feasible or competitive. And then I repeat here what I think is a major objective in particle physics is, if you like, if you want to do a leap in energy range, you should really get to exploring scales, energy scales which are a factor 10 higher. So why LEP3? We think that it is desirable that any backup to FCC, so any plan B, should present fewer technical and or financial difficulties than those associated with the FCC. Because if, as well have a good physics potential. Because as I say, if they have similar technical and financial issues, it becomes another plan A, which is an alternative to FCC, not a plan B. So to minimize the possibility of this, to address the fact this kind of concerns, the LEP3 strategy is to reuse as much as possible the existing infrastructure at CERN, use maximally the R&D which has already been carried out for FCC-ee, means we need, if anything, the same R&D and hardware, and we do the same hardware choices as FCC-ee, and keep the required financing within the envelope of the current budget of CERN. So something which we know we can do. What we think we know we can do is something which we have already done. So you will see that LEP3 financially is similar to the construction of LEP, or if you like, the LHC, when it comes to the famous curve of the combined deficit curve or whatever. You can basically build it, we believe you can build it using CERN budget plus reasonable lending of money. This is not a new possibility, by the way. There was already for not the previous ES strategy exercise, but the previous one, 2013, there were already a couple of papers which have been proposed, which have been submitted, but they were not really considered any further. So from following from those papers which were submitted in 2013, the idea is basically that one could reuse the LEP-LHC tunnel by basically improving compared to what had been done at LEP, having, in other words, the name of the game is to be able to achieve much higher luminosity than what was achieved at LEP. And in order to do so, we are basically profiting from a trick which has been developed with the beauty factories, with the B factories in the past, which is whenever you want to really to go with a plus and minus machine to very high luminosity, the real problem is that you burn the beam very, very quickly, mostly due to Baba scattering effect. And so one idea is basically to have two rings, one which is an accelerator ring where you accelerate the particles and you keep them at top energy and where the collision happens, and then you have a booster accelerator which basically accelerates less particles, but they're always at the top energy, and you basically top up, you inject particles at the top energy. That is because if you don't do that, if you want to achieve order of 10 to the 34 luminosity, basically a field would last 10 minutes. So every 10, 15 minutes, you add a few more electrons. A few more means a few 10 to the 10th. Okay, so that is the idea behind it. In our proposal, we basically pick up these original ideas, and then we also try to save even additional money by proposing to reuse substantial part of Atlas CMS, and you'll see a comment more on that. In 2013, there used to be as well TLEP, which then became FCC, and even then, TLEP and the LEP3 had always a ratio of luminosity which was order of factor 5. So we're not doing things which are extraordinary in this respect. So talking about instantaneous luminosity, this is a curve which you probably have seen already. The curves of luminosity in units of 10 to the 34 centimeter minus 2 seconds minus 1 as a function of energy for the various kind of E plus E minus machine. You can see here we have added the left 3 points. There are the CPC, the FCC, and there is also the LHC. One should point out that, and you will see in all of the tables which I'm going to show you, this preliminary to be checked because, you know, the achievements of, for example, of the linear collider is a moving target. I mean, despite the fact that they've been around for 25 years, 2 weeks ago, they doubled the luminosity that they can achieve, despite not having demonstrated, you know, one of the issues of the linear collider is to have nanometers beams to be controlled over the whole length of the field and whatever. And now they're even doubling the number of, the reason why this point is here and not here, where it used to be, is because they've now added, they've doubled the number of bunches that they think they can work on. But that, so how can we do that? The LHC has 8 arcs and 8 long stretch sections. The length of the arcs is 2.5 kilometers, and each straight sections around the 8 points where the beam could in principle collide are 560 meters long. The inner diameter of the tunnel varies between 3.8 meters in the arcs and 4.4 in the straight sections. The reason why this is important is that one will have to install, you can understand that in a plus and minus machine, the crucial elements are the radio frequency, which are basically providing energy to the beams and compensate for the energy lost by synchronous radiation around the beam. So the RF would have to be installed. We would use all of the straight sections for radio frequency cavities. And this is actually a proposal on how these 2 rings could be indeed be integrated into the tunnel. You can see there's a collider ring below. 1 meter above will be the booster ring, the one which basically accelerates in order to provide the top up of the electrons. And then you can see that there is the room for a possible vehicle, which would be the one which installs the machine. Like you always have to care about the fact that when you do the installation, you need to allow enough space for a vehicle to be able to deploy all of the magnets and all the elements of the machine. So these are LEP3 parameters. I leave them, they are available in the slides, but mostly let me illustrate them a little bit. So one is assuming that one will have 2 experiments. I will tell you why. If you assume that you won't minimize the work, so you reuse, if not the detector, you reuse the Atlas and the CMS Cavern, you will not be able to do 4 experiments because you would need to install them in IPs where you cannot install experiments. If you want, I can elaborate on that later. The highest central mass energy will be 230 GeV. Now, let me tell you why. I didn't discuss this plot. This plot, if you like, is a function of energy showing the cross sections for the production of Z through, associate the production of HZ, which is the largest cross sections in a plus or minus machine. Then you could also have WW fusion and things like that. So that, if you like, in green, there is the total Higgs cross sections. And then there is something which is the effective rate of producing Higgses. Because the fact that you have synchronous radiation losses, you basically have a point where if you limit the amount of radio frequency power you want to give to the machine, and this is the fundamental parameter, we basically are limiting the radio frequency power which we give, which we think we can install, which is essentially the same as FCC-ee, by the way, 50 megawatt of radio frequency power. Then if you do that, you effectively gain by adding more electrons and positrons at lower energy because you lose less, you need less RF power. The RF power compensates for what you lose in terms of synchronous radiation, but you also have to accelerate the particles. So more particles you have, more RF power you need. But also if you go to higher energy, you lose more for synchronous radiation. So there is an optimal. And the optimal essentially has been chosen by FCC-ee. In fact, for FCC-ee, the optimal point is different from LEP3 because being a bigger ring, they have less synchronous radiation losses. So FCC-ee had chosen to run at 240 GeV. We basically have chosen 230 and not the peak, which would be 235, simply because if you go at 230, you basically have 18% lower synchrotron losses while losing only 10% of statistics, but you save 300 million. So essentially that is, you save 300 million in RF, okay? So that you understand why these choices. So we have chosen 230 GeV for the central mass energy. The synchronous radiation power loss is fixed at 50 megawatt as for FCC-ee. So essentially we are going to use exactly the FCC-ee radio frequency system. The loss per turn is 5.4 GeV, and the total RF voltage which we give is 6 gigavolt. So if you like, we have something like 10% margin as for FCC-ee. The instantaneous luminosity is, depending on the energy, would be in terms of units of 10 to the 34, 1.8 at 230 GeV, 6.4 at the WW threshold, and 44 10 to the 34 at the Z pole. We need to have a crossing angle of 30 milliradians. That is in order to be able to have enough bunches and prevent them from interacting elsewhere than the point where we want to collide. So these 30 milliradians have consequences. Running scenario with 20 years program, 6 years at 230 GeV, 4 years at WW, 5 years around the Z, plus more years to do other things if you like. The total estimated number of events would be 4.7 10 to the 5 Higgses versus 6 10 to the 5 Higgses for the ILC 250, or 22 10 to the 5 for FCC-ee, 3.7 10 to the 7 WW, and 1.7 10 to the 12 Z. So this is assuming as well a running time of 195-day operation. In other words, we believe that LEP3 can be competitive with the alternative, is possible alternative to FCC-ee when it comes to Higgs and electroweak physics. And I will go more on that. Why we are so much better than LEP used to be, let me work out through the arithmetics. So we basically, LEP3 increases by order of 10,000 the luminosity which was achieved at LEP. And in fact, it is mostly due to the fact that we make it FCC-like. So the synchrotron power loss that is increased at LEP used to be 0.3 megawatt. It goes to 50 megawatt. So we are definitely adding a lot more RF, leading to an increase of under 60 in the luminosity. In fact, the RF power is indeed a cost item, a key cost item. I will show you in a moment. LEP was limited in number of bunches due to a single beam pipe. The squeezing, the focusing at the IP used to be easy 1 millimeter, like for similar to FCC, while it used to be 40 millimeters of LEP. This gives an increase of factor of 40. The vertical beam parameter was 0.05, while it's going to be 0.11 for LEP3. There is a minus side that the fact that you have this crossing angle gives you the so-called hourglass factor, which is basically making you decrease by a factor 1.3. But overall, essentially, you gain a factor of 1,000. The choice of components. The dipole magnets at the injector, we essentially take whatever was designed for FCC. So one uses the FCC design for magnets with 2 different beam pipes. And then we also take the same approach as FCC, which is of having a dedicated LINAC for the injector. The fact that we basically have a smaller radius and less constraints in terms of emittance, we believe that we can have the injector being factor 2 smaller than for FCC, so having the injection energy at 10 GeV instead of 20 GeV. But this is kind of things, you see this, the kind of things which need to be studied, of course. The choice of component, the RF system, the energy loss per turn is 5, as I said, is 5.1 GeV. We want to install a total of 6 gigavolt, having essentially the same margin as FCC-ee. So for the Z running, we think to reuse the 400 megahertz cavities cryo modules. The beam, because the beam current is too high, to use the 800 megahertz cavities that FCC-ee is FCC-ee has in its design. For WW is running, and for the booster we use the 800 megahertz cavities designed for FCC, and you can see there's been already some attempt to demonstrate that we can in fact locate enough cavities into the straight sections to be able to achieve what we want to do using the FCC-ee cavities. Now, crossing angle. The crossing angle means that there is a need of doing, given that the angles go out and then given the beam go out, and then have to cross at an angle of 30 milliradians, you will one of the cost of civil engineering is that the straight sections on either side of Atlas and CMS need to be widened. Okay, so you have to basically excavate to allow the beam to allow the 30 milliradian. This costs 150 million. But the real problem is that in the present optics developed for FCC-ee, you basically, if you, as I said, if you do a copy paste to LEP3, the beam would be crossing 2 meters off axis. You know, presently the axis of the beam of the tunnel is the same as the axis of the detector. So with the present FCC optics, you will be 2 meters off. On the other hand, we believe that you have alternatives because, for example, for CPC, the optics doesn't is less asymmetric between the two beams, and the optics basically crosses on the axis of the tunnel. So if you basically do a copy paste of the CPC optics, we basically can achieve the fact that the beams would collide in the center. Of course, one would need an optician from accelerator to redo the optics, which to be adapted to this. But we do believe that this should not be a problem. But you will see there are a number of things which, I mean, we are not saying that we have all solutions, that there are no problems with our proposal. There's work to be done, substantial work to be done. Civil engineering, the infrastructure is 40 years old, and some part needs maintenance. In particular, there's a part which is under the Jura, which is already half collapsing, and one would need strengthening it. You know, there is a pressure of water outside this part of the tunnel, which is equivalent to the tunnel being something like 100 meters submarine 100 meters below water. So there's 10 bars of pressure outside. And one would need to re-strengthen them. The idea is to put a inner steel lining. And then one needs, as I said, tunnel widening on either side of Atlas and CMS. Those are the major work to be done. The experiment, the machine detector interface, and the plus and minus machine at those luminosity basically requires that the accelerator gets elements which are very close to interaction point. In fact, the final focusing and the shielding to allow Baba scattering into this machine gets to less than 2 meters from the AP. So if one were to reuse Atlas and CMS, which basically should save the community 1 billion Swiss francs. That is why we plan to reuse Atlas and CMS. You would have to throw away most of the hand caps. You would have to find a solution for integrating the Atlas end cap calorimeter and replace the tracker in the center. But you could reuse the magnets and the calorimeters in the barrel. Okay. And of course, all of this requires studies. Other aspects, the energy calibration. For the Z running, one would use the FCC-ee approach. It is a very smart way. You remember that at the time of LEP, one achieved very good energy determination of the beams by doing resonant depolarization. Now, those resonant depolarization was done in very special conditions, 3 times per year, and things like that. At FCC-ee is proposing something which we plan to adopt, which is to have non-colliding bunches, which are the one which you allow to polarize and depolarize. You can do almost continuous measurement of polarization, depolarization. So one thinks that one can achieve similar resolutions when running at the Z. When you start going to higher energy, the synchrotron radiation losses, which are going to be higher for LEP3 than for FCC, basically at this moment would seem to indicate that we will not be able to have polarization at the WW threshold, even though the theorists of polarization think that one can do things about it. On the other hand, that would be definitely something which we are not assuming at this moment. One would probably have to do like we did at LEP, try to find polarization as high as possible. So it was not 163 GeV, but we found it, I think, at 150 or something like that, and then extrapolating using methods. But anyway, that is a point which needs faster study. The beam energy spread, we assume that at MZ, we believe that to have a value similar to FCC-ee. An important point is sustainability. We assume that all building permission permit for which are in place now for the tunnel and LHC should still be in place. The environmental impact should be minimal, and maybe regulations have changed in between, but we think that this is going to be minimal. As you know, one of the issues of FCC at this moment is really to deal with all of this environmental impact. You have to basically get the agreement of all of the communities where the tunnel is going to go through and things like that. Power consumption, the total power consumptions at the highest LEP3 energy will be 250 megawatt, which is whatever we are consuming today with the LHC. Planned stages, the LEP3 program would have 3 phases: near the Z peak, aiming to record 10 to the 12 Z decays over 5 years, near the WW threshold, aiming to record 2.4 10 to the 7 WW events at the threshold, near the ZH threshold, 230 GeV, aiming to get 4.7 10 to the 5 Higgses. For comparison with other projects, I mean, what I'm going to show you in terms of performances, we have not done, we don't have a community as large as the LHC or as large as the FCC. So we have basically scaled up, simply statistical, the error, essentially the ratio of events. So what can we think we can achieve? And as I said here, there is all things which is to be checked and preliminary, simply mostly because when for example, when you look at the LHC numbers, as I said, they have been a moving target over the last month. So I mean, we have to, eventually we will have a table which is agreed upon by everybody. But at this moment, this is what is the situation as it used to be 1 month ago. And the errors for what concerns the performance of LEP3 is taken from FCC 240 scaled by the luminosity ratio, or by the number of events ratio. 22, square root of 22 divided by 4.7, because at LEP3, we basically think we get 4.7 10 to the 5 Higgs bosons, while at FCC-ee, one gets 22 10 to the 5. Okay. That is assuming 2 experiments over 6 years, while FCC-ee is 3 years for 4 experiments. Electroweak physics, essentially the thing which is dominating there is the bosons and the Ws. The Z bosons is 1.7 10 to the 12 Z bosons and 2.5 10 to the 7 WW pairs. To be compared with FCC-ee, which is 6 10 to the 12 for the Z bosons and 1.5 10 to the 8 for WW pairs. And there as well, the errors have been scaled with respect to the statistics compared to the FCC value. For what concerns the LHC, we basically decided not to quote numbers there because it's now one thing which we are assuming is that if you work at LEP3, you're not going to be less intelligent than if you work at FCC-ee. So essentially, the quality of the analysis and what you can achieve is going to be similar. Okay. So it depends only on the statistics. So this is an example of how long it would take to achieve it. And this is, if you like, has been vetted by people who have been installed LEP, LHC, and luminosity LHC. And I'm going to install luminosity LHC. So you can see the various phases. And essentially, we believe that if one were to take the decision early enough, meaning started building the magnets and then producing the RF in time, one would be operational after 5 years from the stop of LHC, which is aggressive, especially from the financial point of view, but I think it's feasible. The cost. So we used exactly FCC-ee costing methodology, and then you can see what the cost of it is. The accelerator, basically, which is mostly RF, it's 2/3 RF, and the rest is magnet, and the rest is order of 2 billion. The injectors and the transfer lines, the technical infrastructures, the experiments. Now, the experiments, we have divided the cost between CERN and the CERN management has said that in the future, CERN will contribute only to 10% of the cost of the experiments. Okay, so for 2 new experiments, the cost to CERN would be 128 million, while the cost to the particle physics community would be 900. If you instead you reuse Atlas and CMS, essentially it amounts to the cost of remaking the central trackers and modifying the Atlas magnet in the forward. And so it would be much less, 58 and 270 to the particle physics community at large. Civil engineering remained the same. And here we have costed the LHC removal. The reason why the removal costs so much is simply because we have taken into account the fact that you might want to store the LHC magnet in order to make it the injectors for the future proton-proton machine, if needed. So it's not just chopping them off and dumping them. So that is why it costs significantly. So the total cost for CERN amounts to basically 3.2 or 3.1 billion. So we assume that the cost will be well within the standard CERN budget, and let me tell you why. Because I remind you that the cost of the construction of LEP was 3 billion. The cost of LHC was 3 billion, 3.2, 3.3 billion. And if you look, I have it here. This is, for example, is called community budget deficit of CERN. And you can see that this is the construction of LHC. This is Illumia LHC. And we are assuming that this is true. So that by the year 2035, one would have reimbursed the debt the CERN has, and then we'll start accumulating some sort of reserve, which then they would be spending from 2040 onward. You will start spending because you start building RF and magnets. And so one would have very likely a curve similar to this over the years, which you see this will be 5 years, something like this. And then you would basically be reimbursing the debt which you accumulate for LEP3 over the next 6 to 8 years. So, in summary, I repeat: if you read our submission to the strategy group, there is 23 times stated that our preferred option is FCC-ee is just so there's no doubt. So our preferred options is FCC-ee and FCC-hh. But if one requires a backup option, we have obviously been seeing that LEP3 is a backup option. It's probably the best backup option you can have. So compared to linear E plus E minus colliders proposed, LEP3 provides similar luminosity for ZH productions, higher luminosity at lower energy, and options for multiple experiments. at a much lower cost. LEP3 is probably the best backup solution, and it leaves room, by the way, time, budget, resources for further development of the machine that can probe directly the energy from sphere at constituents which are 10 times the central mass energy of the LHC. We have now identified any showstoppers, and we consider this proposal to be sufficiently interesting to deserve further studies. We have also identified important areas that would require deeper investigation before CERN can commit to LEP3. So let me, for example, some of it is here, which is the maximum achievable instantaneous luminosity, what are the implications of a crossing angle, what RF cavities are the most appropriate for LEP3, if the tunnel needs enlargement, consolidation some areas, how easily can it be done, how much time will be needed, and things like that. What procedure derogation are required for the removal of LHC elements, especially for those elements which are considered to be significantly activated, which we have not yet put into the timeline, for example, of dismantling of LHC. What is the optimal injection energy into the LEP3 accelerator? And can we assume that essentially, even in the future, we can have a budget profile similar to what we have had in the past for the construction of LHC and LEP? So this is why I would have liked to see some managers of your community, which I hope they're going to listen to the recording. It would be nice if, besides our contribution, there would be also some national delegations which point out what we think is a duty of the strategy team, of the European strategy team. In fact, most country submissions are definitely going to support FCC-ee and FCC-hh as the next project of CERN. For us, proposing another project as a backup with a similar cost will make little sense. So a reasonable backup should be one that builds upon what CERN already has, its infrastructure, its tunnel, using the R&D already carried out, and the cost that can be financed within its current pluriannual budget. We believe that LEP3 fulfills such conditions. So in our view, an ideal outcome of the strategy would be to give to the next DG a mandate to find the resources for FCC, and giving 2 or 3 years for doing so. And in parallel, recommend that CERN allocates adequate, I would say, is not so strikingly high resources to look seriously into the possibility of LEP3 and have resources to proceed to having a TDR for LEP3 by the mid-30s at the latest. Okay, I think I'm done.